Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. Today I'm going to be discussing and showing you the recent structural load testing we did on a section of the wing. What you're looking at in this first photo is the basic test setup. On your left is a 7-foot long section of the inboard portion of the wing, and then there's the test stand that supports the test rig, and there's a counterbalance beam attached to the wing that goes over to a tree, a very friendly cooperative tree that provides the counterbalance. The counterbalance beam is actually bolted to that tree, and that provides the downward force to counterbalance the load that we're going to put on the wing. The test section of wing does not have any sweep because that is not a critical factor for the components I want to test. This next photo shows the center section of the test rig where the wing attaches to the counterbalance beam. What you see here are the attachment fittings and the two 1/2-inch diameter bolts that attach the wing to the counterbalance beam, and you see the fittings on the counterbalance beam that the wing attaches to, and you see a pivot tube. It's a 4130 chromoly piece of tubing that goes through that counterbalance beam and sits on the test stand and allows the structure to tilt back and forth teeter-totter style, and that puts the test stand strictly in a down load only, so there's no bending loads imparted to the test stand. The steel pivot tube that you see is a component that I'm testing for the final design of the wing attachment methodology. It passes through a 1/4-inch wall thickness carbon fiber bushing, and that whole arrangement is something I'm considering using for the final wing attachment methodology. The fittings that I'm testing that attach the wing to the test rig are a backup design. I know that they're going to be plenty strong enough, but they're a little bit heavy. So I'm actually testing a backup design for the wing attachment, and I'm also testing a potential final design of a wing attachment method that uses that steel tube through a bushing. So I'm getting two jobs done with one test. So I'm going to have a follow-up test that is hopefully the final design of the wing attachment method. If that doesn't work, then I fall back to these large fittings that you see here. They'll actually add 3 or 4 pounds to the aircraft, but I know they will work. And if the final design works out okay, then we go that path and I save some weight. So in this one test, I'm getting several items taken care of. The wing itself, I know that the spar is plenty strong enough. It's been run through other tests, so this test is focusing just on the attachment fittings. This photo shows the leading edge attachment methods. The large plywood plate that my hand is on actually has a hole in it that engages a tube that comes out of the leading edge of the wing. This tube helps transfer torsional loads from the wing into the test stand. We're going to load up the wing on the spar, so there'll be very limited torsional loads. And then there's a lighter colored sheet of plywood on the inside, and that has a screw that runs through it into the wood dowel that's in the center of that leading edge tube. And that prevents the tube from disengaging from its mounting plate and prevents the wing from swinging fore and aft as we run through the tests. Here we're looking at the counterbalance beam and its attachment to the tree. There are a series of 2x4 blocks that prevent the counterbalance beam from moving up and down. Those blocks are held to the tree with large lag bolts. Significantly overbuilt, and of course the tree is going to resist all of the bending forces with ease. With the large root structure system it has, that tree's not going anywhere. The counterbalance beam is two 2x4s that have been bonded to the carbon fiber test structure in the center, and they have the 1/2-inch OSB board on front and rear acting as shear webs. Extremely stiff beam, way overbuilt for the test. We want to make sure that the test structure does not fail prior to any of the fittings that we're testing. I'm sorry I don't have a better photo here. This is a picture of the trailing edge of the wing test section. There's a couple of diagonal braces that are attached to the rear spar, and those braces come up and attach to the counterbalance beam, and these are just helpful in keeping the wing from rotating fore and aft during the test. It's also putting some loads on some fitting design that I'm working on for the rear spar, a very lightweight yet strong attachment method. And this is one way to do a quick little test on those fittings and see how they hold up. This obviously would not be the method for attaching the wing to the aircraft, but it does get a test of the fittings at the trailing edge spar. Here you see some of the most critical components of this test setup. There is a hydraulic floor jack, normally used for automotive work. There's a T-shaped support post, and then there's a cradle that the wing sits in. The cradle transfers the loads over a broad area between the wing and that post that goes down to the jack. So the concept here is that the jack supports the wing while we put the load on the wing, and then I can slowly release the hydraulic pressure to allow the jack to go down and incrementally load up the wing. That way we don't do any accidental overloads as we're trying to stack the bags of concrete mix up on the wing. It was a little challenging as we stacked up those bags, and it got higher and higher. We're trying to lift 52-pound bags of concrete mix up that high. So the whole test rig could have been a little bit shorter, but I was worried about bending. So basically we get the bags loaded up there, and I release the jack stand until the jack disengages from that T-shaped post, and that's when the wing is taking the number of bags used and their location on the wing is determined in advance based on the projected loading of the wing at various G loads. Because the wing is not full span, we have to load the bags inboard, which means that we have to actually apply more weight than the wing would endure in a loaded condition in flight in order to get the appropriate bending at the root, because we don't have the full moment arm. This means that locally the wing is loaded up quite heavily, way more so than it'd ever be in real use. So the shear in the wing and the load on the wing skins is much higher locally. I used a piece of 3/4 inch thick styrofoam between the bags and the wing itself to help spread out the load from the concrete bags. And we tried to load the concrete bags as closely as we could directly over the spar. So it is a compromise here, but the key part is to make sure that we get the root fittings loaded up properly and hope that the wing doesn't fail locally. And it all worked out okay. So a little bit of pad, distribute the loads, and we know that the wing, in terms of shear and local compressive loads, is much stronger than it needs to be. Finally, you will note that we've positioned a GoPro camera at the root end of the wing so that we can capture video of what's happening during the tests, and hopefully we'll get a few frames of any failure that occurs so that I can analyze how the failure occurred and determine if any design changes are needed. So in the next segment, you're going to watch some actual video of us loading up the wing for one of the load cycles. I think we're loading it up to 2 Gs. I had tested 1 G earlier in the day just to proof out the test rig, and my buddy Dave came over and we started working from 2 Gs and on up. And we're going here. Okay, so what I had before on here was one for 4 spaces and then one on the end. We need one all the way down. We need 6 or 7. Okay. 6 or 7 of them. I'm going to go look at the. Space them about a foot apart. 1, 2, 3, 4, 5, 6. 6 bags along the length of the wing. And then 2 on it. If we put a little bit of space in between them, okay, it gives it the 1 foot spacing. Look how close I got those bags. this loading that we're doing here will take it to 2 Gs. This one here. Let me double check the spreadsheet. Hear anything break yet?
Not a peep.
Okay, so this is 1.5 Gs, 1.6. So put 2 more on. One here, one here. Let me see what that takes us up to.
I heard a noise.
Yeah, I heard a little snick. That's 2 G loading when that one goes on. Where did we hear the little click? Do we think? In there. That's where the spar repair is on the bottom. Well, we're ready to test it. Ready?
You ready?
Okay. I'm going to try to let it down as slow as possible.
Taking the slack.
Haven't heard anything break yet.
Not a peep.
We had it up over 2 Gs before in the past. Okay, we've taken the full load now.
Okay.
I have to reposition the jack slightly. There's just a post. So that's carrying 2 Gs. What's bending? Is the wing bending at all? No.
Well,
Or
yeah,
is
it is actually. It was slightly.
It was curved up before because of the brake. I never straightened
Yeah.
when I repaired it. I didn't straighten it, so it had a
It's gone
kink in it.
from. Let's see, was that downward facing dog? It was.
Yeah, I see a little bit of bending out here, I think. Let me look at the... Yeah, oh, you can see it here on the trailing edge. You see the rear spars flexing a little. Because it used to be curved up from the previous damage.
Yep.
Okay, so, well, it takes 2 Gs. Let's take her back up. Please take the weight.
You just want to take some of it?
Just take some of the weight off.
Yeah.
Okay. I'm not sure the jack's going to go low enough this time.
Okay.
We'll find out.
Right. Hey, dog.
Yeah, you might not want to get squished, Charlie.
Or she's faster than we are, so I guess.
That pretty much took the bend out of the wing. I'll go one more there. Come on, Charlie. You got to go in the house. Come on. I don't want you squished. It's now a dog-free zone. I'm surprised to see that much flex at 2 Gs. But it is what it is. Okay.
What, the simulation you did on it didn't show that?
Yeah, that 3D finite element analysis. Okay, so take these to 2 here, and I think 3 and 3. Let me put that in. See where that gets us. That should get us up to about 2.5, I think. Yeah, that's pretty much stop. I think that's center. Perfectly balanced. Are we ready for 2.6 Gs?
Go for it. As I say, standing
Yeah,
back.
stand back. This is about where we failed before. Except it was the root fitting that failed. Okay, that's it right there. That's 2.6. How much bending do we have?
Not a lot.
Not too much more than we had before.
No.
Just a skosh more. I do see the leading edge now. I see a little bit of bending.
Yep.
But that's 2.5 Gs. I think we can safely take it to 3. However, we're not going to have enough travel on the jack.
Right.
So I don't think there'll be. We're almost. The jack was almost bottomed out.
Right. Oh, so let's.
So unfortunately, we're going to have to take all the bags off. I have to cut the post.
Right.
I have to shorten the post.
Yeah.
Unfortunately, which means I have to unscrew it from here, which means we have to take all the bags.
Have another couple of posts we could slip in there.
Oh, I do. Yeah.
Yeah.
No, why don't we just cut a 2x4? And we put the 2x4 here and here.
Sounds good to me.
Okay, good. Then we don't have to take all the bags off. Okay, let me punch in some numbers here. Stand by. Let's see, we got 3 and 3. Let me put 3 here and 3 here. Enter. Okay, all you have to do is add 2 more. Add 1 here and 1 here. We're at 3 Gs. No gust loads.
Yeah, I see the trailing edge falling down faster than.
Then really?
Well, that's where there was a lot of motion.
Uh-oh, I heard some creaking.
Yeah.
It was in the trailing edge fitting back here,
Okay.
I think. Are we loaded up too far aft? We might be. Hard to say.
Well, where's the where's the center of
Center lift?
on the bolt?
Yeah. Of course. I put the bolt right where the lift line is. Duh. Just seems more efficient. Which is here, where the jack's going. So I think we're pretty well balanced. Okay, let's go down a little further. Cover your ears for the expletives.
A large explosion.
Slowly. Ah, we're off. Hey, we made 3 Gs.
Sweet.
Woohoo! Quick, put the jack back under it. I don't see anything. Seems to be okay. How about the pivot tube? You see anything going on the other side?
I haven't seen anything.
Nothing's moved.
Moving or popping or creaking or anything.
Well, I heard one little pop back here. Could have been anything. Okay, we're going to take it up to 3.5. Now? Oh no, this is 3.5 Gs. 3.5?
3.5, yeah.
Don't get hurt. Going down slow. Slow. Okay, that's 3.5 Gs.
My fingers are off.
Okay, I didn't hear anything other than a little creaking. Let me just snug the jack a little. Okay, right there. What's the bending like? Trailing edge is bending a little bit more. Leading edge, for 3.5 Gs, I would expect a little bit of bending like that. Okay, I'm taking the load off.
Okay.
And how come I didn't think of this jack the first time around?
I don't know, but it's brilliant.
Brilliance takes time.
Turns out,
If you live long enough, eventually you're brilliant. First time. Number of mistakes. Okay, so this way, Dave. 1 here, 1 here, 1 here.
okay.
And that'll
creaky.
Oh, that's the wood on the tree. Oh, it's trying. I see what it's trying to do. The popping we're hearing is at the tree. Okay, that's 4 Gs. What do you see going on at the tree? It's trying to pull out from the bottom 2x4. We might want to add one more on the bottom. Not that it really takes any load.
It doesn't look like it's doing anything crazy.
Okay, going, taking the load off. Okay, that was 4 Gs. Got up to 5. Now we're over. Take that one back down to 3. There we go. 4.58 will be the next setting. We only need to add 2 bags. I had a finer tuning.
Yeah.
Woo! Where was that snap?
Somewhere in here.
Staying clear. Going down. Whoa! Where'd it fail?
Top spar cap. Somewhere in there. I think it's inside.
Oh, wow. The wing's fine. We pulled the fitting out of the shear web.
Oh,
Literally.
some of them.
In tension.
The whole
In
thing just
pure,
went.
in pure tension. Just slipped it right out of there. Wow. Okay,
But
that is, but.
you heard that. You can replay it and hear it boom,
Yeah.
boom, boom.
Yeah, for each one of the little steps that went. So the wing would have gone to 4.5,
Right.
maybe 5. No, it's not bending that much.
Yeah.
So it's the. What we're looking at here is the fitting that failed. This attachment fitting was in tension, and the bond line here along this edge and here, and of course same on the other side, and the bonding of this part to the shear web is what failed. This part failed in tension going this way, and it was a failure of the bond line itself. None of the carbon composites failed. It just literally pulled out of its socket. These fittings are not the intended setup for the final aircraft. This would not be terminated here. This fitting would actually be this size, run all the way across to the other side of the cockpit to hold the other wing on. So these fittings are not representative of what would be on the aircraft. These were set up just for the test. Now these failed at a little in excess of 4.5 Gs, about 4.6 Gs in tension on that one. We believe it was a cascade failure. This fitting is stepped down from 3/4 of an inch to 1/2 inch to 1/4 inch, and we believe that the bond failed here first on the thicker section, and once this started to fail, it overloaded the bond back here, so it went boom, 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 and it was gone. It'd probably been wiser to have this straight tapered rather than step down, such that the loading would have to fail the entire bond line all at once. In other words, by making it easy to build, by having the thicker plates come along and not tapering this enough, it allowed stress concentrations that allowed a cascade failure. But that's okay, because that's not going to be used on the actual aircraft. This fitting here, the 1/4 inch thick wall carbon fiber tube that takes the steel tubing pin that goes through here, this is intended for the final design wing attachment, and this worked perfectly. It has no ovaling, it has no dents, it's exactly the same as when we started the test. It suffered no damage or deformation whatsoever. I think this design is solid, good to go for the final aircraft. What I'm going to do next to test this is I'm going to mount a pin in the end here, a long bolt, steel plate over the end, and then wrapped with carbon fiber, cut these off, and this pin will go into a receiving steel tube, and I'm going to jig this whole thing back up again so that I can load the test counterbalance spar up at the end to impart a shear load on this bolt that is representative of flight loads. And then I'll be testing this design of the bolt in the end, the steel plate, and the pivot tube. I believe the pivot tube to be just fine. This will actually, on the final aircraft, rather than being a foot long, it's going to be 1.5 feet long, another 6 inches. So we'll actually load this up slightly less to represent the longer moment arm that the final design will have. I think that final design is going to work out fine. And I'll be able to use this test structure to prove that out. I should be able to do that in the next couple of weeks. And then I can lock down the structural design for the wing attachment.
So there we go. We loaded up a 7-foot section of the wing with about 1,200 pounds of weight. Each bag's 52 pounds, concrete mix and paper. The wing itself, 15 pounds, and then the test equipment out at the end, the cradle and the post, all brings it up to about 1,200 pounds. Never ceases to amaze me what you can do with these composite materials. There we have a section of wing that weighs just 15 pounds carrying 1,200 pounds of load, and it would have gone even more if the test fixture had not failed. So pretty good design, solid for moving forward with, and now it's just a matter of refining the root fittings to try to get the weight reduced a little. So let's go back and take a look at what that wonderful GoPro camera captured and see the actual frame-by-frame failure of the test fixture. You'll see the upper 2x4 and spar cap peel away from the attachment fitting, which begins the failure mode. Happens very fast. It lasts for 2 or 3 frames. And let's take a look at that. Sorry for any vibration involved. We inadvertently placed the tripod of the GoPro camera on the test stand structure itself, causing a lot of vibration. You'll see the failure occur in 2 steps, indicated by spikes in the noise level. At the first spike in noise, you'll see the 2x4 lift up from the spar cap and pull the shear web components away from the attachment fitting. And in the next big burst and the camera vibrates is that fitting pulling loose from the shear web. I have this running in slow motion, but you're probably going to want to go and toggle back and forth because the actual failure lasts about 1 second. So there you have it. Overall, a successful test. We know that the wing is good to at least 4.5 Gs, probably well past that. We'll be actually testing the real wing before the aircraft is flown to make sure that it will carry all of the loads required of it. So thanks for coming and watching another one of my videos. Continue to watch, tell your friends, get more subscribers. If you're not already a patron, please check out my Patreon site. The link is in the description of this video. And I have good stuff coming up on how to do repairs on the wing and then the actual activities of building the wingtips. So thanks for coming and come back again soon. Bye now.